Hello, everyone. Welcome to today's exploration of one of the most captivating phenomena in the universe, the life cycle of stars. Stars are the building blocks of galaxies, and their life cycles are fundamental to understanding the cosmos. Today, we will journey through the stages of a star's life, from its birth in a nebula to its eventual demise, and explore the detailed processes. And stars are born in vast clouds of gas and dust known as nebulae. These nebulae are the nurseries of the universe, where new stars are formed. The process begins when regions within a nebula, enriched by the remnants of past stellar explosions, become gravitationally unstable. This collapse is often triggered by external events such as the shock waves from a nearby supernova explosion or the collision of molecular clouds. As these regions collapse, they fragment into smaller clumps, each destined to become a star. The collapsing gas and dust begin to heat up due to the conversion of gravitational energy into thermal energy, leading to the formation of a protostar. In the core of the protostar, temperatures and pressures become high enough for nuclear fusion to occur. Fusion is the process where hydrogen atoms combine to form helium, releasing enormous amounts of energy in the form of light and heat. This energy creates an outward pressure that balances the inward pull of gravity, and a new star is born. The initial ignition of nuclear fusion marks the transition from a protostar to a main sequence star, a stable period during which it spends the majority of its life. During the main sequence phase, a star fuses hydrogen into helium in its core. This phase can last for millions to billions of years, depending on the star's mass. For example, our own Sun is currently in the main sequence phase and has been for about 4.6 billion years. It is expected to remain in this phase for another 5 billion years. The balance between gravitational forces and the outward pressure from fusion reactions keeps the star stable and shining brightly. Main sequence stars come in a variety of sizes and colors, from small, cool red dwarfs to massive, hot blue giants, each with its own unique characteristics and lifespan. Stars of different masses follow different evolutionary paths. Low-mass stars, those with less than half the mass of the Sun, burn their fuel very slowly and can remain on the main sequence for tens to hundreds of billions of years. In contrast, massive stars, those with several times the mass of the Sun, burn through their fuel much more quickly, often exhausting their hydrogen in just a few million years. The lifespan of a star is inversely proportional to its mass. The more massive a star, the shorter its lifespan. Eventually, the hydrogen in the star's core will run out. For a star like our Sun, this means it will swell into a red giant. In this phase, the outer layers expand and cool, giving the star a reddish appearance. The core contracts and heats up, allowing helium fusion to begin. The star undergoes several stages of fusion, creating heavier elements such as carbon and oxygen in its core. The outer layers of the red giant are often ejected into space, forming a beautiful shell of gas known as a planetary nebula. This process contributes to the enrichment of the interstellar medium, seeding it with the elements necessary for the formation of new stars and planets. For massive stars, the end of the main sequence is even more dramatic. They may undergo multiple rounds of fusion, creating heavier and heavier elements until iron is formed in the core. Fusion of iron does not release energy, leading to a catastrophic collapse of the core and resulting in a supernova explosion. A supernova is one of the most powerful events in the universe, briefly outshining entire galaxies and producing shock waves that can trigger the formation of new stars in nearby clouds of gas and dust. The incredible energy released during a supernova can also synthesize elements heavier than iron, such as gold and uranium, which are then scattered throughout the cosmos. The fate of a star after it has exhausted its nuclear fuel depends largely on its mass. Low to medium mass stars, like our Sun, will shed their outer layers and leave behind a hot core that becomes a white dwarf. Over time, this white dwarf will cool and fade away, becoming a cold, dark remnant known as a black dwarf, although no black dwarfs exist yet because the universe is not old enough for any white dwarfs to have cooled that much. White dwarfs are incredibly dense, with a mass comparable to that of the Sun but a volume similar to that of Earth. They represent the final evolutionary state of stars that are not massive enough to become neutron stars or black holes. For stars much more massive than the Sun, the supernova explosion can leave behind a neutron star or, if the core is sufficiently massive, a black hole. Neutron stars are incredibly dense objects composed almost entirely of neutrons, with a mass greater than that of the Sun, but only about 20 kilometers in diameter. They have incredibly strong magnetic fields and can emit beams of radiation that sweep through space as the star rotates, observed from Earth as pulsars. Pulsars are fascinating cosmic lighthouses, their regular pulses providing valuable information about the physics of extreme matter and the nature of spacetime. Black holes, on the other hand, are regions of space where gravity is so strong that not even light can escape. They can continue to grow by absorbing mass from their surroundings, including gas, dust, and even other stars. Supermassive black holes, millions to billions of times the mass of the Sun, are found at the centers of most galaxies, including our own Milky Way. The life cycle of stars is a continuous process. The materials expelled by dying stars enrich the interstellar medium with heavier elements, providing the building blocks for new stars and planetary systems. This process of stellar recycling means that the atoms in your body were once part of a star that lived and died long before the Sun was born. Thus, the death of one generation of stars paves the way for the birth of the next, creating a cosmic cycle of life and death that has been ongoing for billions of years. This continuous cycle of birth, death, and rebirth drives the evolution of galaxies and contributes to the dynamic and ever-changing nature of the universe. Stars also play a crucial role in the evolution of galaxies. The energy and elements released by stars influence the interstellar environment and can trigger the formation of new stars, contributing to the dynamic nature of galaxies. Understanding the life cycle of stars helps astronomers learn about the history and future of our own galaxy, the Milky Way, as well as the broader universe. From the smallest red dwarfs to the most massive supergiants, each star has its own unique story, contributing to the rich tapestry of the cosmos. Thank you for joining us on this journey through the life cycle of stars. If you enjoyed this video, don't forget to like, share, and subscribe for more fascinating insights into the wonders of the universe. Keep exploring, and until next time, keep looking up at the stars.